Hi, welcome to the second video in this series of video tutorials we have designed on how to set up a federated learning pipeline using Flower for simulation. In the first video, we show you how you can set up your Python environment for simulation using Flower. In this video, we're gonna start designing one of the main components in any simulated federated learning setting, which is the dataset, and in particular, how we are going to partition this dataset so each client in our experiment gets a portion of this dataset. We will be presenting a simple partitioning scheme, which is known as IID, but throughout the video we'll make some comments highlighting other ways you can partition this data to mimic more realistic settings where data might be heterogeneous between clients. Remember, you can find all this code linked in the video description of this video. So without further ado, let's start with the tutorial and follow along with the code you can find in the Flower GitHub. So we're gonna be doing all this from here in the main. So ideally we will want to get a function that will return us different dataset partitions for all the clients that are going to be participating, as well as a global dataset, whether it is a validation set or a test set, that can be run on the server in order to assess the performance of the global model after every round, for example. So for this experiment, what I would be expecting is to get something like a train loaders, validation loaders, and then test loader. And this will be called from a function that we can call maybe prepare dataset, for example. And this function will be created in a new directory that we can decide next where it is. Not a new directory, a new file, sorry. So let's get a new file. We are going to call it dataset. And this new file, this new script, is going to first implement this function, def prepare that. For now, we are going to keep it, we are going to assume that it doesn't have any requirement in terms of input arguments, but we will add some arguments eventually. And the first thing we want to do in this preparation process is to actually get a train and test set of MNIST. So we can do this like so: train set, comma test set equals get MNIST. And now we just need to define what this get MNIST function look like. So for example, maybe we want to parameterize where this data set should go. So you can something like this, which I often like to copy all these data, especially if these are small data sets, in the same directory as the rest of my code. So, but in a subdirectory called data. And then we're going to just get a train set from torch vision. So from torch vision datasets, import MNIST. So we're going to pass the path, data path. Is it train? Yes. And then download. We want to download it in case it's not there. And then we need to pass a transform. So this transformation is going to transform the format, whatever the format of the dataset is, into something that can actually be passed through the network. So I'm going to define a very standard transformation matrix, and that transformation function, which is going to be called tr, for example. Let me just make this a bit wider. So this tr is going to make use of other classes in torch vision. So from torch vision transforms import, we're going to be using to tensor. normalize, and then because we want to stack these two transformations, we need to use compose. So we're going to use compose, which expects a list of transformations. First, we're going to do toTensor, and then normalize. And for normalization, recall that MNIST is a grayscale dataset. So the mean and the variance is enough if it is a single scalar. So I have the values written down here, 0.1307, and then for the standard deviation, 0.3081. So that would be good for us. All right, so now we make sure just like this. And now we can get the test set in a very similar way. Data path, train is going to be false, download true, transform dr. Normally you would use a different transformation for your training and your test set, SPED, particularly because you probably want to do some data augmentation in your training. For this example, to keep things simple, we're not going to do any data augmentation, so the transformations for both the training and test set are going to be the same. Also, MNIST is a very simple example, so as long as our model is not too big for the task, I think it will be okay. But we'll be overfitting eventually. And here we're going to return these two datasets. Alright, so this will ensure that our datasets are downloaded or loaded if they are already downloaded. Now what we need to do is to partition this dataset, because there is here, so far we have a single train set and a single test set. We want as many portions of the trains, we want to split the train set into as many portions of clients as clients we have. So first we need to know how many clients there are. So I'm going to set this input argument as num partitions. It's going to be an integer. We might want also to do to have a validation set per client. So we are going to set as a variable called val ratio. What's the ratio of validation? The ratio of examples put aside for validation. It's going to be a float, and I'm going to set it by default to 0.1. And because this function, we want it to return data loaders instead of just data sets, we need also to know what's the batch size we want to use. So I'm going to set it up here, batch size, and I'm going to assume all clients will use the same batch size, which I think is a fair enough assumption. All right. Okay, so now we need to start partitioning our dataset. But the first thing we're going to do is to decide how we're going to partition it. This is a very active debate and research topic in machine learning, in federated learning, how to partition our data. You can take just you can sample uniformly all the classes and obtain partitions in this way. So every partition will have instances of every class. For example, now that we are doing image classification, some other methods of partitioning the data don't follow this IID procedure. Instead, they would say, okay, I want to make the federated learning setup much more challenging, or potentially much more realistic. I want some clients to have only examples of certain classes, at most, for example, 3 classes. Or I want clients to have potentially all the classes, but they are not all, the histogram of labels in a client is not uniform. Like some classes have many more examples than others within the client. So there are at least 3 big flavors of how to partition this data. One is IID, which is what we're going to be doing today. Another is non-IID, following a LDA partitioning scheme, where you can control the non-idness with a single scalar. And then there is another way which is often called pathological partitioning, which says, okay, I want to split the data into this many clients, but every client will have at most 2 or at most 3, at most n labels out of the m total labels. So these are just 3 of the most popular methods of splitting the data, but we're going to be using the simplest setting for this example. So for this, we're going to use one of the built-in functionality in PyTorch, which is called random split. So for that, we need to first import it. From torch utils data, import a random split. And now that we're here, we can import also data loader because we will need it eventually. So what we're going to do now is split train set into num partition train sets. One thing we need to figure out first is how big are these partitions going to be. We're going to keep things simple and every partition is going to be equally big. So how big is this? So num images equals to length. So these are the number of images that will go into each partition. So now we can partition our train set like this. Train sets equals random split. We need to pass a dataset, which is train set, and then we need to pass lengths, which should be, in our case, is going to be a list of integers, where every integer tells me the size of this particular partition. So because we want all the partitions to be of the same length, and we need num partitions, we are going to create a list. What name should we give this? Partition len, for example. And this is going to be num images, and we need num partitions of them, because remember that we have the number of partitions is going to be equal to the total number of clients that are in our experiment. Not the total number of clients that are going to be sampled in every round, but the total population size. And this is what we're going to be passing here, partition len. Also, quite relevant is to make use of trying to fix the random seeds. So federated learning, because there are other stochastic processes going on in addition to just random sampling your batches during training. You have random sampling of clients potentially. Fixing all the random seeds is a bit challenging, but we're going to try. So we can set a fixed random seed for this generator. Will be something like this. And we're going to set a manual seed to, for example, 2023. But first I need to import torch. All right, so this train sets is going to be a list of data sets of this length with these mini training examples, each of them. Now what we're going to do is, for every train set, we're going to partition it into train and validation and create data loaders for each of these. So let's say create data loaders with train val support. So we're going to do something like for this particular train set in a train sets. I know the naming here is not ideal, it's easy to make mistakes, but we are gonna assume we are paying a lot of attention so no mistakes will happen. First we need to figure out, okay, how many examples are here? This won't be necessary if we are sure that the number of partitions can perfectly divide the total number of images in our dataset. In this case, we might be using something like 100 clients, which is divisible which can divide the total number of images in MNIST, which is 60,000, into an integer number. But later on, we might change the number of clients, and then this won't be the case. So let's be safe and figure out how many training examples are in this particular partition. So num total, we can do something like train set. How many we want to put aside for validation? It's going to be integer validation multiplied by num total. So how many are there left for training? It's going to be num total minus num val. All right. So now what we want to do is to split this particular train set partition into two partitions, one with num train images and the other one with num val images. So in order to do that, we can follow exactly the same logic as we did here with random split. But this time we're gonna only split it into two. So for that, we're gonna be receiving two sub-data sets. One is gonna be, let's call it for train, and the other for val. Random split. We are going to split train set. Now we need to pass a list of the lengths of these partitions, and we know the lengths, which are num train for train and then num val for val. And we are going to follow the same practice of setting the generator. Normally, you would set a random seed, pass a random seed from here, from the input arguments, but just to keep it shorter, we are not going to do it. So that's fine. All right, so now we have our train set and validation set for one particular client. What we want to do is to obtain the data loader for pointing to this train and validation partition. So for that, because we need to do this for every client, let's create a list of data loaders. So let's first define a list and two empty lists here. Train loaders, val loaders, what I'm going to do is I'm going to say, okay, train loader, append to the list a data loader that uses as data set the for train. It's going to use pad size. Shuffle is going to be true. And let's say we're going to use num workers. This is a small data set. We're going to be using a small model, so we don't have to go too high here, but let's just set it to 2. And we are going to follow exactly the same syntax for the validation. So instead of for train, we're going to use for val and append it to the validation loader. Shuffle, it doesn't really matter, but we are going to set it to false. And we're going to use the same bat size. And that's pretty much it for here. Once we have completed this for loop, we would have one data loader per client for both the training and validation set assigned to this particular client, which is exactly what we want. The final thing to do would be to create a data loader for the test set. And here I'm going to use a bigger batch size because first we don't need to do training, so the memory footprint of this stage would be much smaller than when clients do training. And we want the evaluation of our global model to be as fast as possible, so the majority of the time is spent by the client's training and not the evaluation of the global model. So let's do something slightly bigger, which is totally fine. And then let's now return everything. Train loaders, validation loaders, and the test loader. Oops, I'm seeing here a mistake. Exactly like this. All right, so let me just collapse that. Okay, so I think we are done setting up this dataset script. Let's just import it correctly from dataset. Prepare dataset. What do we need to pass here? we need to pass the partitions, the path size, and the validation ratio. Let's, before going to our config, I'm going to put it here. So this is how our config looks like. So we can pass the number of partitions by doing cfg, which is the name of our config variable, num clients. And then to get the path size, well, we are not setting it from the config, so I'm just going to, let's set it from the config, yeah. Path size, let's set it to 20. All right, so this is how we would be preparing our dataset. So as you can see, what it does is it first ensure that the dataset is there. If it's not there, it will download it. We'll get, in this case, both training and test set. We figured out how many images to assign to every client, and we split the dataset into that many clients following a fairly standard process, which is just IID partitioning. You might want to change how you partition the data if you want to make the scenario more challenging. And if you are curious about different ways of partition your data, you can search with the keywords data heterogeneity federated learning, and you will get a ton of papers showing you different ways of partition this data and how to prevent problems that appear when the datasets are partitioned in unexpected ways. Because remember, these datasets live in the clients, and the server cannot see this data whatsoever. So the server doesn't know that, oh, this client has instances of all the classes in my experiment, or only has training examples of one label out of 10. The server doesn't know anything like this and cannot know any of that. So in a realistic federated learning setting, when you deploy federated learning in the wild, you would expect that some clients, like some users, have data following completely different distributions. So if you want to make your experimental setup more challenging, this will be the first place to look into. But let's first, before we finish with this section, let's first try run the code and see what happens. What I would expect it to happen is that the dataset is going to be downloaded and it's going to be partitioned. And if we put a print statement here, and if there are no bugs in the code we wrote, we should be able to see that the number of train loaders is going to be 100, which is the number of clients we have here. And if we print the length of the one train loader, let's say, we should be able to see that is something like 540. Let's see. Okay, so yeah, exactly what I was saying. This is not a complicated setup, so there is no much room for bugs. So as you can see, we ran the code, we printed the config as we showed earlier in the previous section of the video. The MNIST dataset is not present in my system because this is the first time I ran the code. So it was downloaded and extracted. And then it did the preparation of the dataset. And here you can see I was printing first the length of this list that contains train loaders. There are 100 clients, so there are 100 data loaders. And then I'm printing here what's the size of the dataset of the first data loader. Remember, all the data loaders point to a dataset partition of the same size. And in this case, it's 540 images. And you might ask why this number in particular? Well, the train set has 60,000 images. If we divide it into 100, that's 600 images. If we then put 10% aside for validation, that leaves only 540 images for training. And for example, before we end this section, let's clear all this. Let's say that we want to change the number of partitions because we want to change the number of clients. So you could go here to the config and change it, but Hydra makes something fairly easy, which is one of the benefits of header, which is that you can change this parameter directly from you can override the parameter directly from the command line. In this case, you will say num clients, for example, equals of 108 images. Why less? Because we have the same data set, which is MNIST, and we need to partition into many more partitions, which results in smaller images per client. So with this, we are done regarding the dataset preparation. So we have ensured that the dataset can be downloaded if it's not present. And we have also, because we are using a dataset that is not pre-partitioned, we have to design our own partitioning mechanism. In this case, we are using a very simple approach, which is to uniformly partition the training set into as many clients as we have. As I discussed briefly, there are other ways to partition this data, which might make the federated learning experiment a bit more realistic. But that's content for a future video.